2.12 Isovectors and the Y-M Lagrangian. Let G be a Lie group with Lie algebra G. An isovector 11 to the A is a G-valued scalar on a manifold M. A gauge transformation G of X acts on an isovector field 11 to the I by the adjoint representation. See equation 2-156. This transformation law is equivalent to saying that 11 is the pullback 11 of X equals 11 bar of B of X to M of a G-valued scalar 11 bar to the A on B. Saphosting 11 bar of BG equals G inverse of 11 bar of G. What is the gauge covariant derivative? In analogy with electromagnetism, write see equation 2-157. Thus see equation 2-158.
More explicitly, let B dot to the C be a vector tangent to B of lambda. Its horizontal projection, B sub the absolute value of to the C, is tangent to the horizontal path B sub the absolute value of lambda through B of 0. Related to B of lambda by B of lambda equals B sub the absolute value of lambda G of lambda, with G of lambda a path through E is a member of G. Then G dot to the A equals a sub C to the A B dot to the C, and B dot to the C D sub C11 is given by C equation 2-159. Thus, see equation 2-160.
Using G dot 11 inverse equals C sub BD to the A G dot to the D of 11 to the I. In other words, the horizontal derivative of an isovector on B is C equation 2-161. And the corresponding gauge covariant derivative on M is then C equation 2-162. Here a sub alpha to the A equals B sub A raised to the star C A sub C to the A is, up to a constant, the Yang-Mills vector potential corresponding to the connection A sub C to the A.
The gauge covariant derivative of an isovector is an isovector because its definition looks at the value of the cross-section B of X at the point X sub 0 where the derivative is evaluated. In other words, if one changes cross-section from B of X to B bar of X equals B of Z G of X, the ordinary derivative of 11 of X equals 11 bar of B of X G of X equals involves the derivative dg of the gauge transformation. The gauge covariant derivative of 11 bar, however, is, along the direction X dot of lambda, the derivative of 11 bar of B sub the absolute value of X of lambda G of X sub 0.
Example 2.22. Show directly from the definition that D sub A 11 to the A is an isovector, that see the next equation. Note that the definition of covariant derivative given above can be used for fields that transform according to arbitrary representations of the group
Y-M Lagrangian solution. Since f sub alpha beta to the A is an isovector, script L script equals f sub alpha beta to the A of f sub A raised to the alpha beta is an isoscalar, and also a space scalar, and is therefore the natural generalization of the electromagnetic Lagrangian density f sub alpha beta of the alpha beta of f. See the equation shown. To find the resulting field equations, note that see the equations shown. Thus see the next equation.
Note that just as delta normal gamma sub beta gamma to the alpha is a tensor, delta A sub alpha to the A is an isovector. The inhomogeneous term in the gauge transformation law drops out if one takes the difference. See the equation shown. Of two vector potentials, so a sub alpha to the A minus A sub alpha to the A is an isovector, and see the equations shown. Is therefore an isovector. Thus see the next equation. By Leibniz, and since D sub alpha equals gradient sub alpha when acting on an isoscalar,
delta I sub y minus m equals the integral from normal omega to of normal dr gradient sub alpha delta A sub beta to the A f sub A raised to the alpha beta minus the integral from to of normal dr delta A sub beta to the A d sub alpha f sub A raised to the alpha beta equals negative the integral from normal omega to of normal dr delta A sub beta to the A d sub alpha f sub A raised to the alpha beta, for variations delta A sub v to the A that vanish at the boundary partial differential normal omega. Thus see the equation shown. And the source-free field equation is see the equations shown. This is the analog of half of Maxwell's equations. The other half, gradient sub alpha f sub beta gamma equals 0, has the obvious analog.
See the next equation, which is also true. For gravity, f sub alpha beta to the A is the Riemann tensor, and d sub beta f sub A raised to the alpha beta equals 0 is the Bianchi identity. Proof of the identity d sub alpha f sub beta gamma to the a equals 0. Start with see the equation shown. Then see the equations shown. Then see the next equation.
And since gradient sub alpha gradient sub beta a sub gamma to the a equals 0. Even in curved spacetime, and with cancellations, see the equation shown, where the last step follows from the Jacobi identity. Example 2.23. For Yang-Mills theory, d sub alpha normal psi equals partial differential sub alpha negative Ig of a sub alpha times normal psi, where A of lambda is matrix A sub B alpha to the A, and normal psi is an isovector, normal psi to the alpha. For different lambda, the matrices A of lambda do not commute, and we need to show that U of lambda is given by see the equations shown. So, in a series expansion of the exponential, the matrices are to be ordered as encountered along the path, the largest values of the parameter lambda being to the left.
Solution for Yang-Mills. D sub alpha normal psi to the alpha equals partial differential sub alpha negative Ig of a sub D alpha to the A of lambda times normal psi to the alpha. Note, for different lambda the matrices A of lambda do not commute non-abelian theory, so we introduce the path ordering. Operator P. We have C the next equation. But if we wish to expand the exponential we must contend with C the equation shown, where normal gamma sub 1 to the alpha equals the integral from 0 to lambda sub 1 of gamma dot to the alpha of lambda d lambda, etc., and a sub alpha to the first equals a sub alpha of lambda sub 1, etc. Then see the equations shown,
where for the square and higher order terms an ordering property enters. Algebraically we have see the next equation, with no ordering prescribed. So it could be see the equation shown. But this ordering doesn't account for the non-abelian character of the variable A sub alpha. This can be resolved easily, see the equations shown. And U of lambda sub 1 asymptotically equals the exp of Ig of a sub alpha to the first normal gamma sub 1 to the alpha for lambda sub 1 infinitesimal. So see the next equation.
Now go another infinitesimal increment from gamma of lambda sub 1 goes to gamma of lambda sub 2 where lambda sub 2 minus lambda sub 1 is infinitesimal. See the equation shown. Continuing in this fashion we see that see the equations shown, where this merely prescribes the proper ordering on the path integral. Under a series expansion such matrices A sub alpha are ordered with largest parameter values to the left. So we have see the next equation. Now, in quantum field theory 9, the mathematical tools to solve this already exist using perturbation theory methods. Since
see the equation shown, with parallel transport along gamma of lambda, see the equation shown. Thus see the next equation. Thus see the equation shown. And we can write, see the equation shown. Now iterating on U of t sub 1 ... see the next equation.
Let's introduce the time-ordered product. See the equation shown, transforming back with bounds of integral appropriately modified for this case see the equations shown.